Hi, my name is Akin Hyatt.
Hi, my name is Lauren McCaffrey.
And this is our Lab 3 summary. In the last lab, we focused our laser down to a spot size of 122 microns. Although this is a decent reduction in size, many applications demand smaller beam wastes. Our goal in this lab is to focus our Heaney beam to a new waste size of 12.2 microns using the same 200mm lens. When imaging Gaussian beams, the new waste generated in image space is inversely proportional to the beam waste in object space. This means that if we use a beam expander consisting of two positive elements, we can increase the radius of our Heaney beam and achieve a smaller spot size. A Keplerian design is ideal since it forms an intermediate image, allowing us to integrate a spatial filter into the design. A spatial filter is an easy way to remove noise in a beam profile. The first element focuses the incoming noisy beam, converting it into the frequency domain. Lower frequencies are mapped closer to the optical axis, while higher frequency noise is mapped further away. By carefully selecting a pinhole aperture, we can block the higher frequency noise while passing the signal through the pinhole untouched. The second lens then performs an inverse Fourier transform, outputting a clean, noise-free beam.
Before implementing and aligning the system, it's important to consider design trade-offs. Apart from the 800mm total track length requirement, the primary design considerations included creating a Keplerian telescope with a magnification of at least 10x and selecting a microscope objective in pinhole combination that cleaned the Gaussian beam exiting the microscope, while also transmitting most of the energy. As seen here, we identified several design combinations and calculated the corresponding optimal pinhole size, telescope magnification, and relative transmitted power using the listed equations. Ultimately, we decided to use a 10x microscope objective, 200mm focal length collimation lens, and 50-micron pinhole, which has the closest magnification and transmitted the most power through as designed. However, we expected the pinhole size to result in a beam with noticeable noise. Taking the ratio of the waste from last week to the magnification of the Keplerian telescope, we estimated the beam should be approximately 10 microns after the 200mm focusing lens.
We first needed to align the 10x objective with the laser. We verified alignment by adjusting the height and x translation of the objective until the output beam lined up with the laser spot location on the wall.
Next, we aligned the microscope objective to the pinhole. The process we used included starting the microscope objective farther from the pinhole and visually adjusting the x and y translation until it was approximately centered on the pinhole and light was transmitted. We then incrementally moved the microscope objective closer to the pinhole and readjusted the xy translation to maximize the perceived output brightness. We knew we were close when a strong airy pattern was observed, at which point we just needed to move the microscope objective closer to the pinhole.
Finally, we aligned our collimating lens of our Keplerian telescope.
Once we knew that the coordinate frame of the collimation lens matched that of the laser and spatial filter, we could optimize the spacing between the microscope objective and lens to create a collimated beam. By observing the fringes on the shear plate, we could tell that the beam exiting the microscope was converging here, collimated here, or diverging here. Finally, we implemented the 200mm focusing lens and utilized the knife edge protocol to measure the ideally smaller beam waste by taking knife edge measurements on both sides of the new beam waste. We again used a microscope to focus on the knife edge and identify the location of the two measurement plane positions relative to the focusing lens.
Here is the resulting knife edge integration data collected both before and after the back focal plane. We can estimate the beam waste for both measurements by finding the difference in knife edge position when the beam is clipped by 84 and 16%. We can calculate the estimated beam waste using the beam profiling algorithm. For our setup, we found that our new beam waste value is about 8.813 microns.